Welcome children to the study of chemical equilibrium of CBSE, ISC and IB courses. The single lecture will apply to the CBSE requirements, to the ISC requirements, to IB requirements, because theory of knowledge has been included in here, and it is divided into two parts. I am going to explain the first part, and as you can see, a chemical equilibrium is a condition in which a chemical reaction and its reverse are occurring at equal rates. For example, ice is in equilibrium with water when the rate of melting equals the rate of freezing. Now, if I lower the freezing point, water moves backwards and forms ice. If I increase the melting point, more ice turns into water. In other words, it is a state of balance. In physics, equilibrium is the state in which all the forces acting on a body are exactly in balance so that the body does not move. It is not only in chemistry. Equilibrium can be applied to state of mind, to the state of doing work, to physics and chemistry, of course, we are doing just now. During sublimation, solid ammonium chloride is in equilibrium with its solid and is represented as ammonium chloride solid, reversible ammonium chloride gas. So ammonium chloride molecules are escaping into vapor because the vapor pressure of ammonium chloride is very high. So it sublimes, does not go through liquid state when heated. An equilibrium reaction or change is always indicated by a reversible sign, which is shown like this. Otherwise, we write it in this manner. So let's proceed. Characteristics of equilibrium. At equilibrium, the rate of forward and backward reactions are equal. Equilibrium is dynamic, though there is no change, there is no increase or decrease in concentrations of products or reactants respectively. The concentrations of reactants and products are the same as long as the equilibrium is not disturbed by addition or removal of substances in the equilibrium mixture, and the conditions I have already enumerated in the point number 2. Equilibrium does not change as long as the conditions of pressure and temperature to which equilibrium is subjected to are not changed. So we should include 2 here. So subjected to are not changed. Law of mass action. We have done this while studying chemical kinetics. The law of mass action, and it would be very necessary if we revisit this idea before we proceed forward. The law of mass action was put forward by Cato Gullberg and Peter Vaj in 1864, building upon the idea of Claude Louis Berthelot regarding reversible reactions. It states that the rate of chemical reaction is proportional to its active mass or concentration of reactants. And the concentration of reactants is always given in brackets. 2 aspects are involved here. The equilibrium aspect concerning the reaction mixture at equilibrium, and the kinetic aspect regarding the rate equation for elementary reactions. Elementary reactions are those reactions which take place in one step. Let us assume a reaction. A compound A reacts with compound B to give compound C and compound D. Then the rate of reaction R is proportional to concentration of A, and the rate is also proportional to concentration of B. Combined together, the rate is proportional to concentration A multiplied with concentration B. Upon replacing the sign of proportionality with equality, we have R equals a constant, it is known as rate constant, into concentration of A and concentration of B. Here, the coefficients are not given, so they are 1. Anything raised to 1 is not shown, so the concentration has been raised to 1 here. It is 1 here. It is 1 here. 1 is usually not shown, so it was omitted while we were writing down the theory. Anyway, the active mass. From chemical kinetics, we have learned that R equals K into A to the power N, where A to the power N, or concentration A to the power N, is known as active mass of A. It is actually the number of molecules that possess energy equal to or more than threshold energy and have proper orientation, that is properly oriented to each other so that they can react. Their active sites are facing each other so that reaction can take place. That is, old bonds can be broken and the new ones can be formed. These molecules collide to make an active complex that breaks down into products after the old bonds have been broken and the new bonds have been set up. The complex separates out into different products. Conditions for equilibrium: only certain reactions achieve equilibrium, and these reactions are reversible. It's very important. These are reversible reactions. All biochemical reactions are reversible in nature. Equilibrium is always attained in a closed vessel, so this is also very important. And that means no substance can enter or leave the reaction vessel. At equilibrium, the rate of forward reaction Rf equals the rate of backward reaction Rb. Theory of knowledge, how all these things developed and came to us. So theory of knowledge, and it is highly appreciated that everybody learns this, though it is only present in IB course, not in CBSE and ISC or state boards, but it is very necessary that we learn theory of knowledge. And let's see, what does it tell us? The theory of knowledge is a branch of philosophy that explores the nature, sources, and the limits of human knowledge. It helps us understand how we acquire and use scientific knowledge, such as the concept of chemical equilibrium. There are many other concepts as well, where we will be applying the theory of knowledge. Chemical equilibrium is a state in which the forward and reverse reactions of a chemical system occur at equal rates, so that the concentrations of the reactants and products remain constant. Here it is very important to say the meaning of chemical system. The system is closed. It is closed. No matter can enter it, no matter can exit from it. And that is why a chemical system has been put into place here in this sentence. It is a dynamic state, meaning that the molecules are constantly reacting, but there is no net change in the amounts of substances involved. Chemical equilibrium can be influenced by external factors such as temperature, pressure, and concentration, which I have enumerated in the earlier slides, according to Le Chatelier's principle. We'll be discussing Le Chatelier's principle a bit later in the second part of the lecture. Now, TOK continues, to understand chemical equilibrium, we need to apply different kinds of knowledge, such as empirical knowledge, which is obtained by observation and experimentation. For example, we can measure the concentrations of reactants and products at equilibrium using analytical methods such as titration or spectroscopy. We can also observe how the equilibrium shifts when we change the external conditions, such as adding more reactants or changing the temperature, pressure, adding catalyst, adding noble gas. Theoretical knowledge, this is the knowledge that we obtain from logical reasoning and mathematical models. So mathematics becomes very important here, as we shall see slightly later. For example, we can use the law of mass action to derive the expression for the equilibrium constant, which relates the concentrations of reactants and products at equilibrium. We also use thermodynamics to predict the direction and extent of the reaction based on the free energy change. All this a little bit later. Practical knowledge, this is the knowledge that we obtain from applying our skills and techniques to solve problems. For example, we can use chemical equilibrium to design. By saying chemical equilibrium, we can apply the principles of chemical equilibrium to design and optimize industrial processes, such as ammonia synthesis or sulfuric acid production. We can also use chemical equilibrium to control and manipulate biological systems, such as enzyme catalysis or drug delivery. The theory of knowledge can help us evaluate the validity, reliability, and limitations of our scientific knowledge about chemical equilibrium. It can also help us appreciate the diversity and interconnection of different forms of knowledge in chemistry and other disciplines. So interconnection of many disciplines is also possible, and all are interconnected. Physics is connected to chemistry, chemistry is connected to biology. All these three are connected to commerce, you see. So there is nothing in isolation. Now here we introduce mathematics. So introduction of mathematics to equilibrium. Let us consider a general reversible reaction, A moles of A. In the earlier slide, we did not take A moles of A, but it is not always that we use 1 mole. So let us assume that A moles of A react with B moles of B and form an equilibrium with C moles of C and D moles of D. So the rate of forward reaction can be written as RF, rate of forward reaction, equals Kf, which is rate constant for forward reaction, into concentration of A raised to the power A and concentration of B raised to the power B. And the same applies to the rate of backward reaction. Rb equals Kb multiplied by concentration of C raised to the power C, that is number of moles of C, and concentration of D raised to the power D, which is the number of moles of D. At equilibrium, as already mentioned, rate of forward reaction equals rate of backward reaction. If these two are equal, then these two are also equal. So Kf into concentration of A raised to the power A into concentration B raised to the power B equals Kb, concentration C raised to the power C and concentration D raised to the power D. where Kf and Kb are rate constants of the forward and backward reactions respectively. Or by transposing, if Kb is brought under Kf, then this part will go under this. So Kf by Kb, the ratio Kf by Kb is called Kc, and this is read as equilibrium constant of concentrations. So it is C raised to the power C into D raised to the power D divided by A raised to the power A and B raised to the power B. So this is the numerator and this is the denominator. Now, concentrations of solids and liquids in excess do not change and are therefore considered as unity. That is 1. So relation between Kc and Kp. If the reactants and products of an equilibrium reaction are gases, then it is more convenient to use equilibrium constant of partial pressures Kp instead of Kc. If more than one gas is enclosed in a container, each exerts pressure due to its own concentration, that is called partial pressure, and the total pressure of the system due to all gases is the sum of their partial pressures. And this is said by Dalton. It's known as Dalton's law of partial pressures. Let us assume a gaseous reversible reaction at equilibrium. A moles of A gas, B moles of B gas, reversible. C moles of C gas produces C moles of C gas and D moles of D gas. From ideal gas equation, PV is equal to nRT, or P, if we transpose V on the right side, then we have N by V CRT. N by V RT. N by V is equal to C, as we shall see. N by V equals C, which is concentration. So N by V is nothing but it is concentration. So applying to A, we have partial pressure of A given by number of moles of A divided by volume, which is the total volume of the container, into gas constant R multiplied with the temperature at which the reaction is taking place, which is common for all. Gas constant is common for all. Temperature of the system is common for all gases, and therefore we have PV equals NB by V, which is the volume of the total system, into gas constant R multiplied with T, and so on with PC and PD. So total pressure PT is equal to partial pressure of A plus partial pressure of B plus partial pressure of C plus partial pressure of D. And therefore Kp is equal to partial pressure of C raised to the power C into partial pressure of D raised to the power D divided by partial pressure of A raised to the power A and partial pressure of B raised to the power B, that is moles of CdAb. We now have Kp as already talked of and shown in the previous slide, NCRT to the power C, V is common, and here we need some correction. It is this correction, it should be like this. RT to the power C plus D, and NC by V ND by V, and so on. And this NC by V raised to the power C is nothing but concentration of C, because N by C is NC by V is concentration. NC by V is actually concentration of C under square brackets raised to the power C, which is number of moles of C. So the same applies to ND to the power D, and therefore, because we know that Kc is equal to concentration C into concentration D divided by concentration A into concentration B, so we have Kp equals Kc del N. I hope the first set of instructions in this talk that I've given are enough, and they will lay the foundation for what is going to happen in the second set of instructions and the talk that we are going to have with you shortly. So thank you. Do like, subscribe, and please comment. We need your comments badly to improve on all fronts. Thank you. Have a nice day.